Hello everyone, in previous videos we learned how to create structure on Dynamo and how to perform structural analysis by utilizing robust structural analysis software, and we learned how can we iterate to perform this structural analysis multiple times, which will open doors for optimization purposes. Now we will learn how to do it by using Python. Dynamo allows the users to employ Python scripts within its framework. And as you can imagine, employing Python is much more faster than employing robust structural analysis. That's why it is more suitable for optimization purposes. So in this video, we will learn how to employ Python libraries to perform structural analysis, and we will perform structural analysis by employing AI-based meta-heuristic algorithms and Dynamo. So let's begin. I think everyone now can create this structure. This 2D 10-bar element truss. So to quickly show, here is the nodes that we create for it. Now in this lecture, we will learn first how to employ meta-heuristic algorithms within Python. If you perform the steps explained in pre-lecture activities, you should be able to employ Python scripts and Python libraries inside the Dynamo. So here, basic example of using meta-heuristic algorithms. So these meta-heuristic algorithms can be used for various problems. They are most suitable for combinatorial problems where you need to choose a set of elements from a set of lists. So here we are using Pymo for this purpose. It is an open source Python library. Here there is various algorithms that you can use for your optimization purposes: differential evaluation, particle swarm optimization, and NSGA2, and so on. So we will use this library because it is well designed and working pretty good actually for this kind of problems. First, we need to import necessary libraries. These are the Autodesk libraries, so they are coming whenever you open your Python scripts. These are the libraries that we imported. So here what we are doing is we have a problem. So let's say we have a problem. We have a traveler salesman, and we want him to travel through the cities, right? So let's say it will start from here, and it has to visit every city. What is the shortest path for these travelers, for this salesman? This is the problem, and we can easily solve it by using what did I use here? Differential evaluation, but you can also use other algorithms too. So first you need to import Pymo problem class, then you need to import a sampling method, then you need to import your algorithm and your optimization method, which is minimization. Here you want to minimize the cost for this salesman. So here we are importing the distances, we are inputting the name of the cities, and then we are creating a class, our problem class. This is the most important part of this part. So if you don't know any textual programming language and you don't have any knowledge about what's Python and what we are doing here, it's no problem, because large language models are really helpful in this area. Basically, if you can speak English or German, you can communicate with this large language model like ChatGPT, and it will create you these scripts very easily. Okay, you just need to know the logic. So here the important part is here creating the problem class, because every time the rest pretty much stays same and you have to create your problem class. So here, as you can see, we have to enter number of variables, which we have 4 cities, right? And our objective is to minimize the cost to total cost. Okay. Then do we have any constraints? No, we don't have any constraints, and we have to enter the lower limit and upper limit for the cities. How can I say? Now we're gonna choose the cities with the indexes, right? So 0, 1, 2, 3. Okay, we will create random numbers, and with those random numbers, we will choose a path, which one we're gonna start from and which one we're gonna go through. So we need to create random numbers between 0 and 4. That's why our upper limit is 3.99. Nevertheless, then we have to define the problem. Here we are defining our problem. It's basically if you choose a path, then it is calculating the distances, and based on the distance, it is giving a fitness function to that. For example, here, let's say we go through 1, 4, 2, 3, okay? So what is our fitness function? Our fitness result is 20 plus 25 plus 35 plus 15. So you have to go at the beginning every time, right? 20 plus 25 plus 35 plus 15. So this is our objective function or fitness function. And we want to minimize this because it's the cost. Let's assume it's the cost. And we want to minimize our cost. Here we are doing basically this one. And we are calculating the objective function. And we are defining it here as a matrix. Then basically we are choosing the algorithm that we want to use. Then we are choosing the population size, we are choosing the sampling method, and we are choosing the variant. They are all explained in the website. You can go to the differential evolution, and it will explain all the variables and what they mean, how can you choose them, or you can easily ask them to ChatGPT. Okay, then we are creating our problem, and we are creating our minimization algorithm. So here we are defining basically all the created codes here. First problem, then algorithm, then number of generation, how many generation you want to create this population and calculate it. And then if you want to see the outputs, this is verbose. Then we are clicking the run. First we need to unfreeze that one. Then we are clicking the run, and you are seeing the results here. So each generation, it is creating 20 population because we chose to be like that here. And it will create how many generation? 200 generation, right? Yeah. And after 200 generation, it will give you the best individual decision variable, which means best path here. And also it will give you the best route. It is from Basel, Frankfurt, Stuttgart to Karlsruhe. And shortest path will cost 80 euro or 80 kilometers. Right? This is a very simple problem. As you can see, in the first generation, actually, it found the optimum result because it's pretty simple. But this is to understand how the logic works and how you can create it. So this code, all of them is fully generated by genetic algorithm. I haven't coded any of them. That's why you can also do that, and I will ask you to do that actually in the class. After learning how to use metaheuristic algorithms in our Dynamo script, I will ask you guys to perform structural analysis by using Python libraries. So there's lots of available libraries out there. And also there is libraries for structural analysis. Why do we use the structural analysis within Python, but not robot structural analysis? Because robot structural analysis is taking too much time. As you can see here, we performed like 4,000 analysis for this small problem. It just takes seconds, right? But if you want to do it with the robot structural analysis, it will take days, which is not really useful for our optimization purposes. That's why we are using Python libraries. Okay. So let's see what we are doing here. So as you can see in pre-lecture activities, we are using the library called Pinite FEM model 3D. Okay. So here, first we need to import this library. Then we need to add it to the path. In some computers, you maybe won't need to do that one, but if it gives error, you just do that one and it should work. Also, in these steps, still you should communicate with ChatGPT. If you are having a problem, you should post the problem to ChatGPT and communicate what is the problem, how can I fix that problem, because it is really good at coding. As in all modeling softwares, we first need to define the nodes, right? Here I'm defining the nodes. Then I'm defining the supports. As you can remember from previous lecture, we also have done the same for robot structural analysis. Oh, actually here there's two ways to define these supports. First, you can use one by one. You can define the name, then you can define the restriction. So there is the degree of freedom of the support. Or you can basically, if you have, for example, 100 support, you cannot define them one by one. So you can create a for loop that will basically take the name from your list and create the structural element of support for you. Okay, then we need to define the elasticity modulus and shear modulus, Poisson ratios, density, and then we have to add this to a material named steel. You can change the name. As we are defining, as we are creating a truss, we don't need the torsional constant or other not relative inputs. We just need areas and members. So how do we create members? We are just entering a member name, then we are choosing the nodes. Okay, so for member 1, it will go from 1 to 2. Then we are defining all our members. At the end, we are creating the members like this. So here it will get the name from this list. Again, you can create it like this here, but it will take more effort. So we are just creating it by using for loop. So we are taking the name from here. You have to define first name, first node, second node, name of material, and other inputs. Okay. So here we already create those lists. We will just take them from those lists. We don't need this moment of inertia and polar moment of inertia, which is related to torsional resistance, because we assume that, or in trusses, the main parameters used for calculation stress and displacement are axial force and axial stiffness. Because we assume that our truss members only carry axial loads, tension or compression. So we design the joints as a pinned, meaning they do not resist moments, and no bending or torsion occurs in the members. So we are not using these variables in the calculation or in the analysis. However, we have to enter some value to here, otherwise the library will give error. That's why we are choosing them really small numbers so that they are negligible. Okay, I will move forward here. Like these parts are mostly about structural engineering part. So I hope you already know about those. If you don't know, I hope you will see them in future lectures. After this, we already created our members. Then what we need to do is we need to define releases. Okay, so here, this part is a little bit structural side of engineering, so I won't go too deep into it, but while defining the releases, you also have to define some element to turn around. So if you define all the elements as a pinned connection, then you don't have any member to turn around or connect with. Okay, it won't be stable then. In real engineering models, maybe I can show you one. Yes, here. So here, as you can see, in real-world engineering problems, you always have some stable part that holds the elements together. Then you are adding the pinned connections. Okay, so that's why you have one element to actually connect these two pinned elements. That's why here I'm not releasing all the elements, but I am leaving some elements to actually keep the structure together. Okay. After that, I'm adding some loads. Again, you are defining the name of the loads that you want to employ the point load or nodal load. Then you are choosing the direction, and you are entering the magnitude. Here, the coordinate system is a little bit different than Dynamo's coordinate system. So here we have X, Y, and Z, right? But in this library, we have X and Y and Z. So Z is going deeper. Z is the axis in this direction. Okay, so it is good to keep in mind. So if you want to apply like downwards loads, you will use Fy axis, because this axis is Fy in this library. Okay, then we are entering the model analyze, and it will analyze the model. Then what can we do? We can retrieve the stress values, we can retrieve the moments. As we define the releases for the structure, our moments should be 0. So this is a good way to check it actually if you are doing it correct. Okay, here this part is not necessary. Also this part is not necessary. Okay. Then so you can also retrieve and print the deflections, and at the end you can print the max displacements as a list, and also displacement on node 6 that you can print any displacement on any nodes that you enter here. Okay, then you can calculate the weight of the structure. Actually, it is a mass of the structure, but everyone is saying weight. So how we are doing it? We are multiplying density with sectional area and length of the element, and at the end we are summing them together, and we are getting the weight of the structure or mass. And we are calculating the time elapsed during the process, and at the end we are visualizing it. Let's see. After clicking run, you will get a structure like this. Okay, so you can look around, you can turn it around, you can see your members, and so on. And after closing that one, you should be getting the results. You can Now I am clicking save and run. Let's see the results. So here, if you have a load combination, it's giving some information about it. Here my stresses, as you know, here usually when I was getting educated, we were taught that positive means it is tension and negative means it's a compression, but in America or in American-based softwares, they are using it other way around. So here, negative means compression, tension, and positive means compression. Okay, and as you can see, our moments are 0. Here we are getting our displacements, and at the end, I'm getting the max displacement list, all of them. Here I am getting the displacement only in node 6, and I am getting the weight of the structure. Okay, and analysis took like 0.02 seconds. Okay, again, you can all generate this code by using AI. Oh, important part here is while using Python in Dynamo, you have to enter these lines so that you can read your results from here. Okay, this is an important one. And after creating this script, I will ask you guys to convert it to a function so that you can call it multiple times. So we are defining functions like that. We are defining inputs, and there should be an output. Yeah, this is the output. You are defining this list, and at the end, what you are getting is, for example, instead of clicking run every time, you are just defining a list that you want to calculate. And for example, here there is 3 separate lists. I am defining 3 separate elasticity modulus, 3 separate load, and other parameter, and it will perform the calculation 3 times based on this list. Okay, and it will give me the displacements and weights. So I will ask you guys to do this one in lecture. Again, you're gonna use ChatGPT. It is basically the same thing of this function, but it is just like 2 lines more. And when you run it, you will get a list of results, list of displacements, and list of weight. Do you see where am I going? Like here, we get a list, we get another list. As you remember here, we had to define an objective function, which is minimizing the cost. What can be the objective function in structural optimization? Yeah, it is the weight of the structure. Mostly we assume that we want that our structure is lighter, which means cheaper, which means less money. But in the same time, we want our structure to stand still, not collapse every time, right? So here, we will have some constraints in this traveling salesman problem. We didn't have any constraint, but we will have some constraints here. We will say that, okay, our structural displacement on node 6 won't exceed 0.06. Okay. Then based on this constraint, we will try to get the minimum weight. That's how we're going to optimize the structure. We will keep it safe, and we will try to minimize the weight that has been used for the structure. Okay. All right. After this function, now it is time to consider how we're going to combine it with Dynamo. Because until here, as you see, we have basically run just Python code without combining it with Dynamo, where we can use the Dynamo nodes. We can use the Dynamo nodes for creating the complex structure. Here we are just creating a 10-bar truss, right? So as you can see, there's only 6 nodes. What in real structures, there's more than 6 nodes, and it is getting really complicated if you wanna design it with textual code. But it is always simple to design it with visual programming. So we can design our building in visual programming, and then we can use this information to actually create the model on Python library, as we have done it with robot structural analysis, right? And I will ask you guys to actually do it. Here, there's some codes. They are all generated with ChatGPT, and I would like you guys to do it. Basically, what I'm doing is, here we have a list, right? As you can see, here there is a information about the coordinates of the structure, the nodes and everything, the direction and everything, right? So I will source this information in the code, right? How I'm going to do it is I'm going to define an input, and Dynamo Python, you're defining input like that. So here I'm getting the bars by entering this node. So this will be all the information in the bars. Then I will extract the node coordination by entering this one. This is information. This is important because this is not about Python. This is about Dynamo. So if you write bar.startPoint.x, then it will give you the x coordinates. Okay. Then I will get the end coordinates. Then I will create my nodes by using some simple functions, and I'm gonna do the same. The rest will be the basic same. Okay. This is another task I ask you guys to do. Then finally, we will perform some structural optimization. Here, as you can see, the structure in Dynamo directly created in Python. So if I change some value from here, so if I change, for example, the length of my structure, okay, you will get the name structure in Python and also in the Dynamo. You see? Okay. Now let's move forward. It's the last step. Okay. Let's continue with structural optimization part. Okay, I'm inputting the bars. Again, I'm doing the same stuff. I'm creating a different function for weight, which is pretty simple. I'm creating a function for calculating the displacement. At the end, I'm getting two separate lists, as you remember, displacement and weight. Now I'm creating my problem class. Okay, I want to optimize the sections. I don't know what should be the section cross-sectional area for this truss. So here we have 10 different variables because it's a 10-bar truss, right? Now our objective is lowering the weight. We have here a number of inequality constraints, which is, let's say I want my displacement, all the displacement will be lower than some amount. Okay, so how many nodes we have here? 2, 3, 6. Right? So here my number of inequality constraints becomes 6. My lower bound of the input is 0.1. This cross-section area, it cannot be 0, right? So it's 0.1, and highest, let's say 35. Okay, since we have 10 elements, for each element the section, the boundaries are the same, but you can also assign them differently. Then we are creating our evaluate function. The weight is being calculated by weight function. So we are entering this function will create some random numbers, which are the cross-sectional areas. So it will create 10 different numbers. Okay. So each time we will evaluate these 10 different numbers, they will be our cross-sectional area, and we will get a weight value, as we have done with our function. Then we will get a displacement list with these x values again. And after that, we will assign this displacement and weight as the weight will be our objective function, and the displacement list will be our constraints. Okay, we will see, okay, this element has the weight of 343, but as you can see, the displacement is too high for this element, for this structure. So it is low weight, but it is not feasible. We cannot choose that. We want to have better structures. Okay, then we are creating our truss problem. We are employing the genetic algorithm. Population size will be 50. We will use float random sampling. Here, crossover method, mutation method, they are, as I said, detailedly explained in the library website. You can check it. Also here, the another part is how to handle your constraints. Here, there's also different methods to handle the constraint. One method is just separating the constraint from the objective function. So let's say here our constraint was not, the displacement is not exceeding, like, let's say 2 centimeters. Okay, this is exceeding the 2 centimeters. So we are counting that this structure is not feasible. But also there's another way to do it, which is penalty method. We are saying, okay, this structure is exceeding the constraint, but how much? Then we are normalizing this constraint violation. We are getting a value that is based on how much it violates the constraint, and then we are adding this penalized number to our weight. So if there's too much constraint violation, our weight will get larger and larger. So it won't be that good structure. It will be considered as bad structure, not fit for our problem, right? So there's different methods. You can also read the different methods here. As you can see, we are using here the, I think, epsilon method. Let me check. No, we are using the separation method here. So we are just basically checking if the constraint is being violated or not. Then we are considering if, okay, this is feasible or not. Then our number of generation is 50. And we can see our results here. Okay. So here you are seeing that in each population, there is some structures, okay, individuals. And you are seeing that our minimum constraint violation is 0. So we, in the first generation, we found already the feasible solution. But as you can see, the average is, there is some unfeasible solutions too. And here we are seeing the objective function, average objective function, and you are seeing how it's getting lower and lower. At the end, we are finding some solution after 2500 evolution. And here you are seeing the cross-section area that it suggests. You see this 2 number is really small. And these numbers actually, these 2 element here, because if you actually think about it, the forces are here and here, and we can just remove these 2 elements and structure wouldn't affect that much from these changes. That's why the algorithm is assigning them lower sections. Okay. And we are seeing the execution time, and that's all. So I will ask you guys to create these 5 code in class as a class activity, and you will be evaluated based on these tasks. So I wish you a good day. This is all today I would like to talk about. Take care.